So in the previous day, we came to know about the um, river landforms. Some of them we just started some of the features. Uh, so today we will continue the class, and today mainly we try to understand some of the morphometric parameters related to the fluvial basin. That means some of the mathematical uh, determination of several basically these are very helpful for any kind of other study, say for dam construction. So for dam construction we have to study the surrounding topographical area, and you all know that a dam is basically situated uh, to construct the or to store the river water. So where from those river water came, the discharge or supply of river water, the rock types, also those things have to be considered. And for that, river basin morphometry is a very important part of not only for geomorphology, and it is important for other branches of science also. The first type of uh, morphometrical analysis is known as the hydrograph. Basically, it's a simple biaxial diagram uh, where the discharge, that means the amount of water passing through an area or passing through a point in a unit time, that discharge is plotted against time. So that time may be hours, that time may be days, that time may be weeks, that time may be months, or that may be years also. So depending upon my necessity, if we want to know the daily variation of discharge, we plot in the x-axis the plot here the weeks. Similarly, monthly, seasonal, yearly variations, depending on necessity, we plot here that time in the x-axis. So for each day or for each week, we measure the amount of discharge over a certain area, and thereafter we simply plot a bar diagram here, and after that we draw a free line, that is the frequency curve, which indicates our hydrograph. Now this here in this picture, this green colored line is basically indicating the hydrograph. Now here you can see that there is a peak, there is a point when the hydrograph start rising. This limb is called rising limb, and after that at certain point it reach a peak, that is known as peak flow, and after that again the flow or discharge becomes low, that is known as recession limb, and comes to the normal or base flow, that is the mean flow which is found throughout the year of time. So what does this portion, this rising portion indicates? This rising portion basically indicates an abnormal event. Abnormal event means, suppose throughout a week, in particular one day, the area suffers heavy rainfall. Rest of the days in the week, the area suffers a very low amount of rainfall or nothing. So in rest of the days, the flow through the streams or flow through the rivers is within the base flow, and particularly in that day when the rainfall happens, that day the discharge or the amount of water flow through the stream channels will be much higher. So that is indicated by this peak. Okay, similarly for weeks also. So in some week, the rainfall will be higher. Similarly for seasons also, if you consider all the seasons, in monsoon seasons, there will be high rainfall in an area. So the river channels, they will suffer high amount of discharge of water. That will result this increased amount of this graph. So this is that is why it is called an abnormal event. Similarly, it may happen for storm also, which is not at all a regular phenomenon. That is happened in a once in a year or once in a 2 year, like that. So this graph with time, the amount of discharge indicates, that is known as hydrograph. Now, in this picture, in this left hand side, you must see some blue colored bar. This is basically known as hydrograph. That is, uh, it is the reason for which this hydrograph shows this amount of, or this much peak in this portion. So that hydrograph basically represents the rainfall event or the monsoonal event or the storm event. So this is the abnormal event due to which this high amount of discharge during this time happened. So you may see that the incident between these two events, the peak, if you look at the peak, suppose this is the rainfall and this is the peak time where maximum amount of rainfall occurs, and if you look at the hydrograph, that is the peak flow. So if you observe the incident, that is the rainfall, and the discharge, that is the flow through a channel, there you can see a gap. So basically this gap is to, after the rainfall, all the rainwater have to gather or bring in one channel by the natural flows due to the action of gravity. So that requires some amount of time during which there will be normal flow. When those rainwater gathers into the channels, then the hydrograph starts increasing, and after some time it shows peak flow again. After some the peak flow, after some time the flow starts decreasing. That is the indicated by the recession limb. So the difference between the maximum amount of rainfall and the difference between and the point of maximum amount of flow, this time difference is known as basin lag time or simply lag time. So that is basically the time difference indicating the peak of rainfall, that is the peak of the cause, and the peak of the flow, that is the peak of the effect. So that is the difference between cause and effect peak values. So when a graph is plotted indicating both the flow and the rainfall, that is the cause, then it is a mixed curve showing both cause and effect. The flow is indicated by hydrograph and the rainfall is indicated by hydrograph. That is this blue bar diagram. You can join these bar diagrams through a frequency curve also. Okay, so basically this picture is a mixed biaxial diagram. Now, why should we construct, or why should we study, or why should we analyze hydrographs? There are mainly two reasons. First, to find out the amount of flow through a particular place, and ultimately the amount of flow through the entire drainage basin occur during certain interval of time. Secondly, it helps us to predict the abnormal events such as flood, and therefore influence implementation of flood prevention measures. That is, during the flood time, often peoples are moving far inland from the river channels. That is, they move to a more safer place so that they cannot feel the effect, or they are not suffer the effect of flooding. In flood, you know that many of the wealth or many lives are destroyed by those abnormal events. And ultimately, these two are done for any kind of construction construction like any kind of civilization, that is houses, buildings, or any kinds of dam, or even it is done for irrigation purpose also, that is during which time our crop field will get ample amount of naturally flowing water, and which time it is required to supply water through the artificial canals for fulfilling the demand of crops. So it is the need for ourselves to become safe and to construct any kind of construction for our own purpose. We have to study the discharge through a channel with time. Now, depending upon the time unit, hydrographs can be classified as four types, as I already told you. The first one is annual hydrograph, where the discharge is considered in yearly cycle. The second one is monthly hydrograph, where discharge is um, drawn or discharge is measured in monthly cycle. Third one is seasonal, here season is considered, and the fourth one is flood cycle, flood hydrograph. So here we are only considering the abnormal event, we are only looking before and after the flood. The rest of the time of the year or the rest of the time of the season, we did not consider uh, the hydrographs. So only the flood time, during which there will a high amount of rainfall or a massive storm hits an area, due to which there will be high discharge of water, that part is only considered in flood hydrograph. Now, coming to the river types, uh, there are two characteristics by which river can be classified, and the two characteristics are, first one is sinuosity and the second one is multichannelness. Sinuosity is the ratio of along channel distance between 2 points and the shortest distance between the points. So if we consider this is a channel and we consider 2 points A and B, so for measuring sinuosity, we have to uh, measure the distance or the length along the channel, that is the scarp path distance have to be measured, and we have to measure the straight line path, that is the shortest distance from these 2 points. So this curved channel path divided by the shortest straight line distance between the 2 points is known as sinuosity. Okay. Now, a river having greater amount of sinuosity will be of meandering river, where a river having less amount of sinuosity will be a straight river. Like sinuosity, another morphometric parameter is the multichannelness. Multichannelness means the number of individual smaller flows within the channels when uh, we try to observe in cross section of the river. That means when we observe from one bank to other bank, if we count the number of individual smaller flows within the channel, suppose in this picture this is number one, this is two, this is three, this is four, this is five. So there are numerous smaller channels within the large river channel. These are the smaller flows, and in multi-channelness we have to uh, count, we have to measure. So in multi-channelness we just counting the number of these smaller channels across the stream, that is indicated by multi-channelness. Okay. As much as higher values of these smaller channels are found uh, in the cross section of the river, that river will be braided river, and that means that river which are multi-channeled, and those channels are separated by a by bars, and where the channel number is less or becomes one, that means that is a single channel river. Now, depending on the values of sinuosity and multi-channelness, here in the y-axis multi-channel, sorry, we put the values of sinuosity, and here in the x-axis we put the values of multi-channelness. And this multi-channelness term, in many books you will also get multi-channelness is similar to braiding parameter. That means number of braids, that means number of those small channels across the river. And of course it is measured for a particular unit distance. Suppose it is measured for say for 10 meter, or it is measured for say for 100 meter. So within a fixed distance, how much or number or how many number of channels are there across the river. Now, if we plot this multi-channelness or braiding parameter in x-axis and sinuosity value in y-axis, uh, the first quadrant having low sinuosity means the value is less than 1.5. Okay, and the braiding parameter or multi-channelness is less than 1. Okay, so if these two criteria satisfied, that means sinuosity value less than 1.5 and multi-channelness is less than 1, then the river is straight river. Whether in this quadrant, when the sinuosity value is less than 1.5 but braiding parameter or multi-channelness value is greater than 1, then the channel is known as braided river. Similarly, in this quadrant, the sinuosity value is greater than 1.5 and uh, the braiding parameter is less than 1, then the river is meandering river. And in this portion, it is a mixture of meandering and braided river. That means it shows higher sinuosity values, that means greater than 1.5, and braiding parameter or multi-channelness value greater than 1. So depending on these two parameter, all sorts of rivers found in nature, they are grouped into these four divisions: straight river, braided river, meandering river, and anastomosing river. So now there will be no confusion which river you called which terminology. For which river you will call meandering, or for which river you will call anastomosing, or for which river you will call braided river. So that there will be no arbitrary things. Instead of that, we can express all those various types of rivers in terms of some mathematical values. Now next is the stream ordering. So, stream ordering is whenever a smaller stream meets with other stream, then two smaller stream when meets with each other, it makes higher order stream. That means when the two rivers water meets with each other, then after meeting the point, one point, the entire water of those two rivers are now flowing through a single channel. So definitely after meeting, the amount of discharge will increase and increase as the river meets with other rivers. So therefore, for knowing the discharge of water, or for knowing the strength or other parameters of any river, stream ordering is very important. Now, for stream ordering, there are mainly two methods. One is given by Strahler and other is given by Shreve. In Strahler method, it is numbered as such as the unbranched fast river. the first any unbranched river is numbered as 1. So you can see any unbranched river, this one, this one, this one, any unbranched river, that means it will not meet with any other river, completely unbranched, that is numbered with first order river and number as 1. Now when two first order river meets with each other, it will make a next higher order, that is second order river or second order stream, indicated by 2. When two second order river meets with each other, here you can see this is a second order river formed due to meeting of two first order river. Here it is a second order river. When two second order river meets with each other, it forms the next higher order, that is third order river. So right, this way the numbering goes on. So whenever two same order river meets with each other, after meeting, the followed river will be of next higher order. Okay, but when a higher order river meets with a lower order river, then the stream order remained what is the higher order river was. That means when here you can see the second order river meets with the first order river. This one is the second order river and this is the first order river. When these two rivers meets at this point, then the higher order numbering that retains. That means after meeting with the first order river, the river becomes or the river retains its higher order numbering. That means it still a second order river. When two second order, similarly here you can see that is a fourth order river coming. It meets with the second order river. So the higher order numbering retains. That is, it is fourth order river. Similarly, fourth order river meets with the first order river, higher order retains. That means it is still in the fourth order river. So Steller method says that the unbranched river is demarcated as number 1 or first order river. When two same order river meets with each other, it forms the next higher order river. When one higher order river meets with the lower order river, then the higher order number retains. That is the main methodologies for numbering following the Steller method. Now, Shreve uh, indicate or propose another method in which he mainly considered the magnitude of the river. So like Steller method, Shreve also proposed that any unbranched river is marked as number 1, that is the first order river. But when one river meets with the other river, then these two numbers together they are added. That means here you can see the two first order river meets with each other, that is 1 plus 1, 2. Now in this case, here it is a first order river and here it is second order river. When these two meets, according to Shreve method, it becomes 2 plus 1, that is third order river. Similarly, here it is a 15th order river. When these two meets, this 3 plus 15, it becomes 18. So in Shreve method, it basically indicates how much amount or how much river it is made in the entire river basin. So 18 means that a higher number of smaller streams are meeting with each other to form this to form this main stream. But in case of Steller method, we cannot estimate the magnitude of the river, that is how many number of smaller streams are added with each other and form this stream. But in Shreve method, you can get an idea about the magnitude of the river. So between these two, uh, in our daily practice, Steller method is the most followed methodology for numbering or for ordering natural rivers or streams. Next comes the drainage basin morphometry, some other measurable things within a drainage basin. So to note the other measurable parameters, first you have to know what is drainage basin. So drainage basin is an area within which water is supplied by precipitation and it is transferred to the ocean. So the entire area in which water or the entire area from which water is supplied to a channel. Okay, so that entire area which by some way uh, feels the effect of rainfall or feels the effect of the flow within the channel. That entire area starting from its source to the mouth where the river meets with the permanent water body, this entire area is known as drainage basin. Now a river during its journey from its source to the mouth, a river, we know it erodes the sedimentary rock. Now up to which level a river can erode? That level up to which a river can erode, that is the level of the permanent water body, that means the level of the top surface of the permanent water body. In our daily practice we know the permanent water body is mean sea level, so almost all river meets with the sea. So the top surface of the sea level, that is the mean sea level, that is the level up to which a river can erode. So that level is known as base level. That is the level up to which a river can erode. And below this level, below base level, depositions start. Now, an interesting thing is, or a funny thing is, uh, ocean is a permanent water body where river can meet. So the mean sea level, that is the 0 meter sea level, is our base level. Now, many rivers meet with a large lake situated inside the continent or is situated far within the continental landmass. So, for those rivers, what will be the base level? For those rivers who does not meet with the sea, instead of that, it meets with a uh, intercontinental or land within land a large lake body, that is also a large body of water. For those rivers, the top surface of the lake water is the base level. So in your exams, you may or you may find this type of questions that name a permanent water body and a temporary water body, or name a permanent base level and a temporary base level. So for permanent base level, your mean sea level is the permanent base level, and a temporary base level is the top surface of the water level of a lake. Second is the measuring of stream length. Stream length is the length of the river along the curvilinear path, along the channel, along the curved channel over which the stream flows. The measurement of that length is known as stream length. Now, if a river have many tributaries, so the total length of the river indicates the measurement of all the lengths of all the tributaries. So if a river have n number of tributaries, that means summation of n number of lengths for all tributaries gives us the total length of the river. So the total length of the river is indicated by LU, that is equal to L1, L summation of L1, L2, L3 like that up to Ln. Okay. The stream length measures the average length of a stream in each order. Now, if you want to know the length of the first order streams, only you want to know the length of this first order stream. Here L1 means all the length of the all first order streams. L2 means length of all second order streams. Similarly, Ln means length of all nth order streams. Now, if you want to know the total length of first order streams, so simply your L1 will be answer. That is measuring the curvilinear length or curvilinear path of all the first order streams. Similarly for L2. Now, if we want to know the mean length of first order stream, then by clubbing, suppose L1 X, suppose you have two first order streams which is demarcated by X and Y, L1X and L1Y. These are two first order streams. These twos are clubbed, then divided by the number of first order streams. So in this case, my first order stream is number is 2. So I clubbed together the length path of the L1X and L1Y and divided them by 2. So that gives us the mean length of first order stream. Similarly for other order streams also. Okay, so that is the mean first order length. Similarly, means second order stream length, mean third order stream length, and ultimately, if we try to measure the mean stream length, that is the mean LU, then we have to again club the for mean LU, we have to add mean L1 plus mean L2 plus mean L3 to up to mean Ln. So all the mean values, mean length values of different orders, they have to be added to get the mean length of the stream. Next is the stream length ratio. Stream length ratio can be defined as the ratio of the mean stream length of a given order to the mean stream length of next lower order. So suppose you are um, you are told to estimate the mean stream length between second order and first order stream. So for determining stream length ratio, always you need two successive mean stream length of two different successive orders. That means either you need first order or second order, or second order or third order. So it should have two successive orders. You cannot measure the stream length ratio of comparing the first order with the third order stream length. So it always have first order with second order, second order with third order with fourth order with fifth order, like with this. So two successive stream orders are required to determine the stream length ratio, and the formula is LUR is equal to LU, that will be the mean length of the higher order. That means if it is second order, that is the L2, and the denominator is again L2 minus 1. That means it is the mean length of the lower order, immediately lower order. That means L2 by L1. So in numerator, it will be the mean length of second order stream. In denominator, it will be the mean length of first order stream. Similarly, if it is between third order and second order, so in numerator, it will be mean length of third order stream divided by mean length of second order stream. That will give the stream length ratio. Next is the drainage density. That is how much drainage or how much amount of uh, channel is there in a given area. So drainage density is a measure of how frequently stream occurs on the land surface. As I told you that within this given area, uh, what is the number of the streams, that is how much flows a given area suffers. Now it reflects a balance between the erosive forces and the resistance forces of the ground, obviously, because until or unless the flows cannot erode and form a permanent channel, there will be no flow, channelized flow. There will be a sheet flow. So for forming a river, the flows should erode the underground rock uh, and form a permanent channel. So obviously, it shows a relation between the nature of the rock as well as the erosive force of the flowing water and the resistance force of the rock over which it flows. And obviously it will also depend on vegetation also, and climate, lithology, um, all things are factors for determining the drainage density. Now, in mathematically, drainage density can be estimated by dividing the total length of all streams that we measured previously, that is the LU, and the area of the drainage basins, that is considering all the surface area of the drainage basin in the denominator. So LU, or you can write it as summation of L, total length, divided by summation of A, that is the total area of the drainage basin. That gives you the drainage density of any given area. Next is the stream frequency. It is a measure of topographic texture expressed as the ratio of the number of streams in a drainage basin. So in drainage density, we measure the length divided by area. In stream frequency, we are concerned about the number of streams over a given area. So here we plot, or we write in numerator the number of streams, and in denominator we write the area of the drainage basin. Obviously this is the total numbers of drainage basins, total number of streams of all orders, and the total land area. Next is the bifurcation ratio. It is the ratio between the number of stream segments of one order and the number of next highest order. Stream length ratio, it is given the number of length to the divided by the next lower order length. Here in bifurcation ratio, it is the number of streams of one order, and it is divided by the number of streams of next higher order. So in number of streams, suppose it is number of streams of second order, in denominator it will be number of streams in uh, next higher order, that is it will be of third order. So if I take an example, that is there are number of first order streams in this basin, I count all these numbers. First you have to order all the streams, then you have to count all those numbers. So after counting, it becomes first order stream is 17, second order stream is 6, third order is 2, fourth order is 1. So for bifurcation ratio, it will be 17 by 6. That means N2 by N1 by N2. Similarly, in this case, between second and third order, bifurcation ratio will be N2 by N3. That means 6 by 2. Next is the basin elongation ratio. That means how much elongated, or the opposite thing you can say, how much circular a basin is. So the basin elongation ratio is expressed as the diameter of a circle of the same area as the drainage basin divided by the maximum length of the basin. Suppose your basin is this shape, so it will be like an ellipse. It's a elliptical in shape. Now for an ellipse or any other shape, you can measure the area of the basin. Say for this figure, the area of ellipse pi AB. A is the longer radius, B is the smaller radius. So if you consider it as ellipse, this will be your A and this will be your B. So pi AB is your area of the ellipse. Now what it says, the diameter, the circle having the same area of the drainage basin. So this pi AB, that is the area of this elliptical basin, should be equals to the area of a circle, and we know that the area of circle is pi r square. Now from this equation, pi AB is equal to pi r square, here the only known thing is this R, because this area you can calculate. You have to calculate from your field studies. So the area of the drainage basin you already known. That means this value is known, pi AB. The unknown thing is the area equals to the equivalent circle. That means pi r square. So from this equation, you will get the value of r, that is the radius of the circle. Now, if whenever you get the radius of the circle by doubling it 2r, you get the diameter of the circle. Now that diameter is divided by the maximum length of the basin. So the maximum length of the basin can be measured. Now this diameter, when this diameter is divided by the maximum length of the basin, that will give you the basin elongation ratio. In a simplistic way, many people follow this formula also, and for basin shape, and that is the area of the basin, say for ellipse, that is the pi AB. It is directly divided by the square value of the maximum length of the basin. Okay. And you can see here for a for your for an example, here the RF value, the basin shape indicating value, that is RF, uh, is given for two different shape basins. One is for elliptical, one is for circular basin. You can see that RF value is decreasing whenever a basin is more elongated, whenever a basin is more elliptical, whereas RF value will be much higher whenever is a basin is more circular. Okay, so we can estimate the basin elongation ratio by following this method, and this is the more scientific method according to the definition, or you can estimate the basin shape by this method. But here this RF is not the basin elongation ratio actually. So for measuring basin elongation ratio, you have to go through these formulas, go through these methods. Here you can write it solely by basin shape. Okay. Now, another significant aspect of river geometry is the vertical profile. That is, it means the um, change in altitude or change in height of the river flow path, starting from its source to the mouth. So, say for example, a river started its journey from point A, or suppose in case of Ganga river, it started its journey from the Himalaya, if it is indicated by A, and meets with Bay of Bengal if it is indicated by point B. Now, in different points of the flowing path of Ganga river, we'll note down the distance and plotted it in x-axis, and corresponding altitude values with respect to mean sea level that are plotted in y-axis. So corresponding distance from the source and height with respect to mean sea level are noted for each point, and they are plotted in a biaxial diagram. So in x-axis it is the linear distance its origin to the source, and in y-axis it is the altitude or height or elevation. So if we get all these points starting from its source to its mouth, and we join them with a free line, we will get this kind of um, curvy linear or concave up linear diagram, which is the longitudinal profile or long profile of the river. So it basically indicates the change in elevation of a river through its uh, journey path. Similarly, you can draw the cross profile of a river. That means the change in elevation from one point of one bank to other point of other bank across river. that can be also drawn. So in that case, it is known as cross profile. And when the change in elevation or change in height is plotted with respect to the total journey path of the river, it is known as longitudinal profile and long profile. Generally, for most of the rivers, it shows this kind of concave up profile. Next is known as the neck point. That is the point where a certain change in the slope is observed. If you follow the longitudinal profile, the river profile should be following this path, and after reaching this point, the profile certainly, or the slope of the river path certainly changes. From the gradual slope, it certainly becomes very high, very steep. So this certain change in slope, certain change is stream gradient, um, is started from a point, and that point is known as neck point. Basically, it indicates the differential rock type into different areas. Maybe this area's rock profile is much more prone to erosion, much less resistance to erosion, whereas these rock types are much more resistant to erosion. So that is why these rocks are less eroded and these rocks are much eroded. If these rocks, the rocks of this area will be same of like this, then the profile will be like that. It will follow the um, previous slopes. But due to the change in lithology or due to change in geometrical structure, suppose this area is highly faulted, so that faulted becomes a structure and becomes a weak zones within the rocks, along which erosion will occur more intense way. So due to that, erosion will occur more, and ultimately the base level of the flow path will be lowered compared to its uh, natural one. So the junction point from which this kind of certain change in or break in slope of the river is observed, that point is known as neck point. Mostly it is observed for faulted country rock, in which certain drop in elevation within the channel flow path are observed. Next is the drainage network. You may all know about these different types of drainage networks. The first one is the dendritic, where it shows a spreading tree-like pattern with an irregular branching of tributaries in many directions at different angles, and it mostly occur, or it mostly found on uniformly resistant strata, uh, or unconsolidated sediments, or homogeneous igneous or metamorphic rocks. In those types, that means in homogeneous country rocks, you will find this kind of drainage patterns. The second type is the parallel drainage network, which displays regularly spaced and more or less parallel uh, streams with tributaries joining at acute angles. It develops where strata are uniformly resistant and the regional slope is marked in one direction, and there is a strong structural control um, by the faults or joints to have or to govern this kind of drainage pattern. The next type is the trellis, where the dominant drainage direction and the secondary direction, if you see, this one is one drainage direction and the secondary direction, and from it the secondary direction, these are mutually perpendicular or at right angles to that each other. So the primary tributaries join the mainstream at right angles, and the secondary tributaries almost run parallel to each other. You can see this one is the secondary tributary that is joining the primary tributaries at right angle, but the secondary tributary is almost parallel to the mainstream. This kind of drainage pattern is found in an area where there are alternating bands of hard and soft rock stratus, or it is often found in folded terrains. Next is the radial drainage pattern. Here the streams flowing outwards in all directions from a common centrally elevated part. It is mostly found in the topographic areas where there is a dome that from the central peak or central elevated portions, the uh, streams or rivers diverged in all directions. It is also found in some volcanic cones. So for the volcanic cone, the streams diverged in all directions. The next type is centripetal drainage. Here the streams flowing towards a central depression, that is the basin, and it mostly found in volcanic craters or volcanic calderas, craters, or any kind of tectonic basin into which streams from all directions come towards this common point and meets the central depression. Next is the annular type of drainage network. Here, the main stream arranged in a circular pattern, more or less circular pattern, with subsidiary streams lying almost right angles to them. This kind of drainage pattern is found in a dome basin morphology where erosion concentrically uh, or erosion removed the exposure, and in the basins or the rock types, they are arranged concentrically. So the rocks are basically, it's a dome like structure previously, and now it is eroded, so the rocks are now oriented in this manner, rock types, the lithologies. Now, if the dome portion, that is the elevated portion, is eroded away, so all the rock types are now exposed. Now, as all the rock types are exposed, suppose it is a rock type, it is B, it is C. So all these rock types are exposed to natural agents. Now, due to their difference in lithology, they suffer differential erosion. So for that, the stream channel network should be in a circular pattern, which is known as annular pattern. And the last type is rectangular drainage network. It almost similar to the trellis pattern, that is streams and their tributaries joining each other in right angles, but it is less regular than trellis, and it is mainly controlled by the structural phenomena, that is the rock must be severely faulted or jointed, and due to the structural control uh, they have this rectangular pattern of drainage. In contrast, in trellis there are alternating soft and hard rock, so there is no structurally controlled drainage network. It is soft depending on the hardness of the different rock types. And the rock types, hard and soft rock, arranged in an alternate fashion. Whereas in rectangular type, the rock types, whatever may be the rock types, it may be soft, it may be hard, but they are intensely faulted or intensely jointed. So those structural features control these kinds of drainage network pattern. So for today, that is all. We'll continue the landforms, or we'll continue different work done by rivers during its journey path in the next successive classes. Thank you.